In today's video, we'll learn about elastic potential energy. So when does an object have elastic potential energy? So if we have a compressed or a stretched spring, we say that this spring has potential energy, and that this energy that is stored in the stretched or compressed spring, or any other elastic material, is called elastic potential energy. And we can calculate our elastic potential energy by the equation that states that 1/2 of our spring constant multiplied by our displacement squared is equal to our elastic potential energy. And so this elastic potential energy, like all the other potential energies we have learned about, is a conservative force, so that the total energy of the system remains constant. So if we were to have a block that was attached to a spring that was compressed, our spring would have elastic potential energy, and as the spring was released, that potential energy would then be transformed into kinetic energy, which we can see is summarized in our equation of our conservation of mechanical energy. Since the total energy of the system is equal to 1/2 our spring constant multiplied by our displacement squared, we can take the sum of the kinetic and potential energies at a particular position to solve for our velocity, where 1/2 our spring constant multiplied by our amplitude squared is equal to 1/2 our mass multiplied by our velocity squared plus 1/2 our spring constant multiplied by our displacement squared. And once we rearrange this equation to solve for v, we get the following equation, where k is our spring constant multiplied by a, which is our amplitude squared, minus our displacement squared, divided by our mass of the object. So we're given an example that states that a child's toy consists of a piece of plastic attached to a spring. The spring is compressed against the floor a distance of 2 centimeters, and the toy is released. If the toy has a mass of 100 grams and rises to a maximum height of 60 centimeters, estimate the force constant of the spring. So if we summarize our information that we're given, we see that our displacement of the spring is 2 centimeters, that the mass of our object is 100 grams, and our object change in its y displacement reaches a total height of 60 centimeters. And we're asked to solve for the force constant of the spring. So using our conservation of mechanical energy, we see we'll have translational kinetic energy plus our potential energy due to gravity plus our elastic potential energy of the spring, initially equal to our translational kinetic energy plus our potential energy of gravity plus our potential energy of the spring at its final point. Well, first we can simplify this equation, since initially our object hasn't been displaced, so our potential energy due to gravity will be equal to 0, and our object has yet to move, so our kinetic energy will also be equal to 0. If we look at its final state, we see that at the top of its displacement in the y direction, its velocity will be 0. Therefore, our transitional kinetic energy will be equal to 0, and that our spring is now at its equilibrium point, so our potential energy of the spring is also 0. So now our equation has been simplified down to the potential energy of our spring initially is equal to the potential energy of gravity at the top of its projection point. And so we can expand our equation now, knowing that the potential energy of a spring is equal to 1/2 our spring constant multiplied by our displacement squared is equal to our potential energy of gravity, which can be expressed as our mass multiplied by our gravity times our change in height. So since we're trying to solve for our spring constant, we can rearrange our equation where we'll get K by itself, which will give us the equation that 2 times our mass multiplied by our gravity times our change in our displacement in the y direction divided by our displacement squared. So we can plug in our values given our mass of 100 grams, which must be converted to kilograms. So if we move it 3 decimal places, we'll get a mass of 0.1 kilogram multiplied by the acceleration due to gravity of 9.8 meters per second times our displacement height, which will be 0.6 meters, divided by our displacement of the spring squared, which will be 0.02 meters squared. And so when we calculate this out, we see that our spring constant will be equal to 2,940 newtons per meter. In our second example, it states that an automobile having a mass of 1,000 kilograms is driven into a brick wall in a safety test. The bumper behaves like a spring with a constant of 5.0 times 10 to the 6 newtons per meter and is compressed 3.16 centimeters as the car is brought to rest. And we're asked, what was the speed of the car before impact, assuming that no energy is lost and the collision with the wall? Yet again, we'll start by summarizing the information we're given. We're given that the mass of the car is 1,000 kilograms and that the bumper acts as a spring with a constant of 5.0 times 10 to the 6 newtons per meter, and the spring is displaced a distance of 3.16 centimeters, and at the end of the collision, the velocity of our car will be equal to 0 meters per second. And we're asked to find what is the initial velocity of the car before impact. So since it says that no energy is lost, we can use our conservation of mechanical energy once again, which states that our translational kinetic energy plus our potential energy due to gravity plus our potential energy of a spring initially is equal to our translational kinetic energy plus potential energy due to gravity plus our potential energy of the spring at its final point. So first we can simplify our equation since initially the car has a velocity, so we have kinetic energy. Our car is traveling only in its x direction, so there's no change in its y displacement. And before impact, the bumper remains uncompressed, so our potential energy of spring is equal to 0 as well. After our collision, it states that our final velocity is equal to 0, therefore there will be no kinetic energy. And once again, the car is traveling in the x direction, so there will be no potential energy due to gravity. And at impact, the spring is compressed, so we'll have elastic potential energy. So now we'll have an equation that our initial kinetic energy is equal to our final elastic potential energy of the spring, which we can expand the equation where we know that kinetic energy is expressed as 1/2 our mass multiplied by our velocity squared equal to our elastic potential energy, which states that 1/2 multiplied by our spring constant multiplied by our change in our displacement squared. So since we're trying to solve for our initial velocity, We can rearrange the equation where we get our velocity by itself, which will give us the equation that the square root of our spring constant divided by our mass multiplied by our displacement will be equal to our initial velocity. So if we plug in our values that were given, we see that our spring constant had a value of 5.0 times 10 to the 6 newtons per meter divided by a mass of 1,000 kilograms taken to the square root multiplied by our displacement in meters, which will be 0.0316 meters. And when we multiply this out, we see that our initial velocity would have been equal to 2.23 meters per second.